Hi, in this video, I'm going to go through the AQA AS-level AS chemistry paper. This is the 2020 paper. This is paper 2. And this is the second half of the paper. I covered the first half in an earlier video. Okay, so ethanedioic acid is a dicarboxylic acid. Draw the skeletal formula of that. Well, first of all, I think I'm going to draw the normal formula of it. So you've got a carboxylic acid at one end, and you've got a carboxylic acid at the other end. So as a skeletal formula, we're going to write that as like this. Like that. Okay. Right. Ethanedioic acid 7.2 is formed by the oxidation of ethane 1,2-diol. Okay. Say suitable reagents and conditions. So all you're doing is we're oxidizing an alcohol to a carboxylic acid, and we're doing that at both ends of the molecule, which is a little bit unfamiliar to us. We're used to just doing it, one functional group per molecule. We're just doing it at both ends. Right, to do that, what you need to do, well, this is a primary alcohol. You need to oxidize it, so we need acidified potassium dichromate solution. Now, you do have to state here the conditions, right? You would need to heat with reflux, because if you didn't reflux it, you'd only oxidize it. Primary alcohol, you remember, first of all, it goes to an aldehyde, and then second step of oxidation goes to carboxylic acid. So you need to make sure you refluxed it in order to get the carboxylic acid. Okay, so ethanedioic acid reacts with an excess of sodium hydroxide to form the salt sodium ethanedioate here. Okay, a student mixes so much ethanedioic acid with the sodium hydroxide, show that the sodium hydroxide is in excess. So first of all, let's do the moles of ethanedioic acid. That's equal to the concentration times by the volume. The concentration is 0.4 and the volume 10 centimeters cubed, so it's 0.4 multiplied by 10 over 1,000. That is equal to 4.0 times 10 to the minus 3 moles. Let's work out the moles of NaOH now. Remember, we're going to need double the moles of NaOH. We're going to need at least 8, at least double that, in order to be in excess, because 2 moles of NaOH per mole of ethanedioic acid. So that's concentration times volume as well. The concentration is 0.2, and the volume is 50 centimeters cubed. That is equal to 0.01. Right, now, the amount that you would need would be 2 times that, which would be 2 times 4.0 times 10 to the minus 3. That's equal to 0.008. Right, we've got quite a little bit more than that. So the sodium hydroxide is in excess. Secondly, calculate the mass in milligrams of sodium ethanedioate that you can form. Right. So I'm just going to rub this bit out here. Now, if we look here, the moles of ethanedioate you've got will give you the same number of moles of sodium ethanedioate. Okay. So the moles of the sodium salt formed, that's going to be equal to 4 times 10 to the minus 3. So the mass of the sodium salt is going to be the moles times by the MR. Right, what's the MR of sodium Eethanedioic, well, that's going to be equal to 2 times 23 for the sodium, plus 2 times 12 for the carbon, plus 6 times 16 for the oxygens is equal to 134. Okay, so the mass of the salt then is going to be 4 times 10 to the minus 3 multiplied by 134. That gives us 0.536 grams. It wants the mass in milligrams there, so times it by 1,000, 536 milligrams of salt. Okay, here's an equilibrium question. Okay, so hydrogen can be made by reacting with ethanol with steam. Okay, give an expression for Kc. So we put the products on the top. So Kc is going to be the concentration of carbon monoxide squared multiplied by the concentration of hydrogen to the power of 4 divided by the concentration of ethanol multiplied by the concentration of water, both to the power of 1. Right, what's going to be the units of that? Well, on the top line, we've got to the power of 2 and to the power of 4 there. So we're going to have mole per decimeter cubed to the power of 6 there. On the bottom line, we've got to the power of 1 to the power of 1. So that's going to be mole per decimeter cubed to the power of 2. And that simplifies to mole per decimeter cubed to the power of 4. Multiply that out, we get moles to the 4 dm 3 times 4 minus 12. That's the units for that. Right, table 4 shows the amount of each substance in an equilibrium mixture. And the container of the volume is 750 centimeters cubed. You have to be careful here not to put in the moles into the Kc expression. Of course, it is in this Kc expression here, we need to put in the concentrations, okay? What does concentration equal to? Concentration is equal to the moles over the volume, which I'll just call V. So I'm going to put that in there. Okay, so let's do that. So we get Kc is equal to, right, the ethanol, sorry, the carbon monoxide, so that's 0.1 over V all to the power of 4. And then the hydrogen, that's 0.22 over V all to the power of 2, divided by concentration of ethanol, which is 0.075 over V, multiplied by the concentration of water, which is 0.156 over V. Right, we know what V is. V is 750 centimeters cubed. That's 0.75 dm cubed. But what I'm going to do is just cancel some of those V's out first of all. So you get Kc and multiply out that bracket. So we get 0.11 to the power of 4 over V to the power of 4, multiplied by 0.22 to the power of 2 over V to the power of 2, divided by 0.075 over V, multiplied by 0.156 over V. Well, you can see that I can cancel out 2 lots of V there. So I'm going to get rid of that V squared and that V there. Okay, and now I need to put in the real value of V, which is 0.75 dm cubed. I'll just do that. 0.75 to the power of 4. Now I need to put all those numbers into a calculator. Do that, and you get 7.65 times 10 to the minus 3. And the units of Kc, as we said before, are mole to the 4 dm to the minus 16. You could, of course, at this point here, you could put all the V's in if you've got a graphics calculator. It's quite easy to do. But I'm a bit old-fashioned and I haven't got a graphics calculator, and so that's the way I would do it. Okay. Right, the pressure of the equilibrium mixture was increased by reducing the volume. Okay, predict the effect of increasing the pressure on the equilibrium yield. Okay, so let's have a look at this. We have got 2 moles of gas on the left-hand side of the equation, and we've got 6 moles on the right-hand side of the equation. So if you increase the pressure, the equilibrium will move to the left, fewest gas moles side. And so that means the equilibrium concentration, yield of hydrogen, will be lower. Drops. Okay, now predict the effect of increasing the pressure on the value of Kc. And this is a trick question, right? You know, because we know that the the Kc expression is equal to H2 to the 4 CO squared over C2H5OH H2O. So the temptation here is to jump in and say, oh, well, we've got less of the hydrogen, okay? So that means the number on the top is smaller and the number on the bottom is bigger, so Kc should get smaller. That's the temptation, but the correct answer is no effect. There is no effect on the value of Kc. The only thing that changes the Kc value will be to change the temperature, and we're not doing that. Okay, you change the position of the equilibrium, but you don't change the position of Kc. That's all you need to say. Okay, but if you're wondering why, it seems a bit strange. Well, it's because you're doing 2 things at once here. You're changing the number of moles of hydrogen. Yeah, that's reducing, but also you were doing something to the volume, aren't you? You're changing the volume as well. And both of those things means that Kc doesn't change. You don't need to say that in your answer. You just need to say this. So no effect on the value of Kc, only temperature affects it. But they always try and catch you out with that. Okay. Right, onto the multiple choice section. Statement about thermal cracking. Now, a pressure between 100 and 200 kilopascals is used. And quite frankly, I haven't got a clue what pressure, but that does seem a bit high. And I wouldn't bother learning any particular pressures and temperatures and stuff because they never really want that. So I know in a lot of textbooks and stuff, it does give you precise values and between this pressure and that pressure. I wouldn't bother learning those numbers. Right. More importantly, aromatic hydrocarbons are the major product. That's wrong. You get that mostly with catalytic cracking. A zeolite catalyst is used. That's wrong as well. That's with a zeolite catalyst. Do you break carbon-carbon bonds when you carry out cracking? Yeah, you do always, no matter what kind of cracking. So that is definitely the right answer. And so by looking at that, A is wrong. Okay. And that pressure is probably a bit too high, but I wouldn't know. Right. Statement is not correct about ozone. Right, it absorbs ultra harmful ozone, which of course is O3. Yes, it does absorb UV light. It decomposes form O2 oxygen. Yeah, its decomposition is catalyzed by chlorine molecules. Not quite. It's not chlorine molecules. It's chlorine-free radicals, isn't it? Okay, so that one is wrong. And ozone holes are regions where you've got reduced ozone. Yeah, that's true. So C is the answer there. Okay, now 11, the UPAC name for this compound. Okay, right, and number the carbons 1, 2, 3, 4, 5. So it's pentane. Well, that doesn't really tell us much because they're all pentane in those answers there, aren't they? Yeah. Right, so it's 2,2-dimethyl, isn't it? And it's 3-fluoro. The question is, which one of these two comes first? So I think it's the fluoro because that's alphabetical. F is before M in the alphabet. So it's 3-fluoro-2,2-dimethyl is the right answer there. You've got 2 methyl groups there, so it's 2,2-dimethyl. It's not just 2,2,2-methyl. Okay, what is the name of the major product of the reaction between 2-ethyl butene and hydrogen bromide? Right. Oh, so I just need to rub that off here. Sorry, I've drawn 2-ethyl butene. So if I number that, 1, 2, 3, 4. See, that's an ethyl group on number 2. Right. Now that's going to react with HBr. Now H can stick either onto carbon atom number 1 or number 2. Now in the major product, which one does it go to? It will go to the one that's already got the most hydrogens. A hydrogen goes with its friends. That's why some people say it. You remember it that way. So the hydrogen is going to go on carbon atom number 1, and the bromine is going to go on carbon atom number 2. So it's now tempting to think that that is called 2-bromo-2-ethyl butane, and to say the answer is B, but that's not right, because now we look at the longest carbon chain. We should number it from the longest carbon chain now. So we should be calling that 1, 2, 3, 4, 5. And we treat this thing as a sort of side group, okay? So you can see that it is 2-bromo-2-methyl pentane. 2-bromo-2-methyl pentane. Sorry, 3-bromo, that's not right. 3-bromo-2-methyl. Right. Sorry, 3-bromo-3-methyl. Yeah, that is, because that is carbon atom number 3. Now it's not number 2. D is the right answer there. (13) What can be used to distinguish between these two compounds? Now you can see here I've drawn them out, because when you have formulae written in a line like that, it's a bit confusing to see what's going on sometimes. So I prefer to draw them sort of semi-displayed. Right. Can you distinguish acidified potassium dichromate? We'll oxidize both of them because they're both aldehydes. Yeah, so they'll both change color. They'll go from orange to green. Tollens reagent, well, no, you can't distinguish. They're both aldehydes. They'll both, give a silver mirror with Tollens reagent. They've got the aldehyde group there at the end. The MR at high resolution mass spectrometry, well, that's not going to work. So if you look, they've both got 1, 2, 3, 4, 5 carbons. They're both C5H10O. So they've got identical molecular formulae. So that they will have identical MZ values for the parent ion here. Okay, that's not right. The fingerprint region, yeah, that's always going to work. Molecules always have different fingerprint regions in the infrared spectrum. So that's the answer. Okay, 14 about free radical substitution. An excess of methane reacts with it's important, reacts with chlorine in the presence of UV. What are the main products? Well, if you remember, well, what happens is you generate a chlorine free radical, don't you? That reacts with a methane molecule, and you swap one of the hydrogens. Well, one of the hydrogens goes with the chlorine free radical to form HCl. And what's left behind is a CH3 free radical, which then reacts with the chlorine again in the next step to form CH3Cl and a chlorine free radical. Right now, so we're not going to get H2. So A is wrong, and C is wrong. Which is right out of B and C? Well, D is going to be the right one, because you've got loads of methane and not much chlorine, because the methane is in excess. You're not going to get multiple substitutions. You've got all the chlorine is going to be used up. So you're only just going to get that. You're not going to be able to swap more hydrogens with chlorines. So that is the answer there. Of course, if you used excess chlorine, then the answer would be B. In which reaction does the inorganic reagent initially act as an electrophile? Right. Bromoethane with ethanolic potassium hydroxide. Well, OH minus is never going to be an electrophile, as it's negatively charged. And in that reaction, it's actually not a nucleophile either. It's a base, if you remember, but don't worry about that. Chloroethene with aqueous sodium hydrogen. Again, OH minus is never going to act as a nucleophile. It's negatively charged. It's not that. That's a nucleophile. Ethane with chlorine. There's no electrophile there. It's a free radical substitution. So it's got to be this last one. Ethene with concentrated sulfuric acid. Yeah, that is right. And if you remember why, so you've got your ethene. You've got a high electron density in the double bond. And you have your conc sulfuric acid, which is like this. And that is an electrophile because oxygen here, this oxygen, is delta negative, partial negative charge because it's very electronegative, leaving that hydrogen delta positive, and that is what reacts. That pair of electrons goes onto the hydrogen. You probably remember that mechanism. Okay, so D is the correct answer there. Okay, an empirical formula calculation. Now, so what I'd say is you have got 90% carbon by mass. It's a hydrocarbon, so 10% must be hydrogen. So in 100 grams, we've got 90 grams of carbon, and we've got 10 grams of hydrogen. Right, now we need to work out the moles, which is equal to the mass over the atomic mass, the AR. So that's going to be 90 over 12. So you've got that many moles of carbon. 10 over 1 moles of hydrogen. That's going to simplify to 7.5 moles of carbon to 10 moles of hydrogen. Okay, how are we going to simplify that ratio? I think we divide by 2.5 on both sides of the equation. 2.5 goes into 7.5 3 times. 2.5 goes into 10 4 times. So it's going to be C3H4 is the correct answer, D. Right, which compound has the lowest relative molecular mass? Okay, so right, I've drawn out the formulae of all of those three. And we can probably see straight away, if we compare these two, which one's got the lowest molecular mass? Well, it can't be that one, because that's the same as the other one, except it's got 4 more hydrogens, okay? So it can't be that one, forget about that. Now, let's think about the nitrile. That's going to be 29. That bit's 29 plus 12 for the carbon plus 14 for the nitrogen. That's going to be 55. I think that's going to be the smallest one. Let's do for this fluorine one, right? That propyl group, that's 43, and fluorine is 19. So 43 plus 19, that's 62. And ethanoic acid, well, I know that's 60. So remember it. So it is propane nitrile. C is the smallest one. I suppose with questions like that, it's getting a quick way of doing it. And I would probably think if you don't write out the formulae very quickly, you're much more likely to make a mistake. So I wouldn't try and save time by not writing out the formulae. 18, okay, correct about the production of ethanol as a biofuel. Now, ethanol, you ferment it from, you ferment glucose, which is grown from a plant. You end up with a 15% solution of glucose, because any stronger than that will kill the 15% solution of ethanol. Any stronger than that kills the yeast, and the yeast all dies. So then you have to do fractional distillation to get 100% ethanol. Okay, let's see about that then. So biofuel is produced by the fermentation of glucose in the presence of yeast. Yes, but not air, because it needs to be anaerobic. That won't work. You'll get aerobic oxidation of the glucose if you do that. That's wrong. Bioethanol is purified by fractional distillation. That's true, because I said here, yeah, you only get 15%. No carbon dioxide is released when biofuel ethanol. Of course, you do get carbon dioxide when you burn anything with carbon in it. Biofuel ethanol burns with a cleaner flame. That's not true at all. It's the same stuff, same chemical. So B is the answer there. What is the minimum volume of aqueous bromide needed to react completely with that much butadiene? So let's draw the structure of butadiene. So you've got 4 carbons and you've got 2 double bonds. Okay, that's butadiene. Put hydrogens on. Now, when you react that with bromine, you're going to get one Br2 molecule is going to add across here. And you're going to get another bromine adding across there. So what is important there is it's 2 moles of Br2 to every 1 mole of butadiene. Right, let's work out the moles of butadiene then. That's going to be mass over mR. The mass of butadiene is 0.2 grams, 0.02. They give us the mR there. They say it's 54. That's equal to 3.7 times 10 to the minus 4. Now, we said earlier, for every 1 mole of butadiene, you need 2 moles of bromine. So the moles of bromine is going to be double that. Two times 3.7 times 10 to the minus 4. That's equal to 7.4 times 10 to the minus 4. Now we need to work out the volume of bromine solution. So volume is equal to moles divided by the concentration. So that's 7.4 times 10 to the minus 4 over the concentration, which they tell us is 0.05. Which is equal to 0.0148 dm cubed. Okay, but it wants it in centimeters cubed, so times it by 1,000, you get 14.8. So B is the correct answer there. This is the sort of, if you forget to forget there's 2 double bonds, you put that answer down. And if you got the ratio the wrong way around here, you'd end up with that one. And then if you didn't have any clue at all, you'd write down D. Okay. Right, which statement about the molecules in a sample of gas is correct? Right, this is about the Boltzmann curve, so that's why I've sketched it over there on the right, and you can see that this green line that's a low temperature, and the red is a higher temperature where the average energy of the molecules all increases. Now, A, at a given temperature, all the molecules move at the same speed. That's definitely not right, okay? You get a distribution of speeds, don't you? Right, at a given temperature, their average kinetic energy is constant. That's a funny way of putting it, but that is actually true, but it just seems a bit odd. That is the answer, but let's just check. C, as temperature increases, there are more molecules with the most probable energy. Now that's not true, right? The most probable energy, let's look at low temperature. That's the most probable energy there, isn't it? Okay. At high temperature, that's the most probable energy there. Now you can see the peak of the higher temperature one, the red one, is to the right, but it's always got to be lower because the total area under the curve, which is the total number of molecules, will got to be the same. So you can see that, look, as you increase the temperature, there are less molecules with the most probable energy. So that is wrong. Right, and let's see D. As temperature decreases, there are few molecules with the mean energy. Now, the mean energy, these are different colors, kind of messy, but the mean energy isn't quite the same as the probable energy because the curve is asymmetrical. The mean energy is probably about there. Yeah, that's for the green line, and for the red line, it's probably about there. And you can see that also decreases at higher temperature. because the height of the red curve is lower. So B is our answer there. That's quite an unusual question, that one, the Boltzmann curve. Okay, right, here's a tricky Hess's law question here. Okay, enthalpy change data are given here. Okay, and what we've got to do is we've got to find out the enthalpy change for this reaction. Okay, so I've written this out on the right hand side here. And we're going to have to construct a Hess's law thing. Okay, now we've got 2 bits of our Hess's law cycle, and we need to work out what to put in the other. Now I think you can probably see the other thing we're going to do is we're going to put down carbon solid and H2 gas. So can we write that down there? So, all right, now we're going to put my arrows. Okay, so I'm going to put in, right, let's put an arrow in blue. Right, what are we doing there? Well, we're turning, well, have we got that? Yeah, we've got that one there. Look, as you see, that's what we're doing there. Carbon and hydrogen forming methane, and we're going to put the arrow that way, and the energy change for that is minus 75 kilojoules. Okay, let's see, let's draw this one here. Now what we're doing there, well, we're breaking up 2 molecules of hydrogen to form 4 molecules of hydrogen atoms. Okay, so it's this one, isn't it? And we've got to double that value there because that's for 1 molecule of hydrogen, so that's going to be 2 times 436, which is equal to 872. That's a positive value. Right, we want to find out this, don't we? Okay, so what we're doing, so let's write down the answer. Equal to, right, we're doing the blue arrow, but we're going against that, so that's going to be plus 75. And then we are going up the green, we're following that, so that stays positive, plus 872. So we work that out, that gives us a total of 947. So it's plus 947 is the right answer. If you were doing this and you got a bit mixed up and you got negative 947, it's quite easy to get the sign wrong. A little common sense check should tell you, well, there's no way that it's going to be exothermic, that reaction, is it? Because you're breaking bonds between carbons and hydrogens. Okay. Okay, so here's about errors in a calorimetry experiment. All right, the temperature changed from 21.8 to 19.2. So I'm going to work out delta T there. So we're going to do 21.8 minus 19.12. That gives us 2.6 degrees Celsius. Okay. Right. And it says the uncertainty of each reading of the thermometer is 0.1. Now we take 2 readings, one for the initial temperature and one for the final. So the total value is going to be, the total error is going to be double that, 0.2. Okay, so percentage error is going to be equal to the error, 0.2, over the measurement we make, 2.6, times 100. That gives us 7.7%. So the answer is that. And of course, that would be the one you'd forget if you'd forgotten to double. If you've got to take into account that you're making 2 readings with the thermometer. Okay, and I think this is the last question. Okay, an experiment is done to determine the enthalpy of combustion of a fuel using a calorimeter containing water. All those things. Which expression gives the enthalpy of combustion? Assuming there's no heat loss. Okay, so I'm going to write down then the equations we're going to need will be Q is equal to MC delta T. We also need delta H is equal to Q over N, which is the number of moles. And also we're going to have N, the number of moles, is equal to the mass of the fuel burnt divided by the MR of the fuel. Okay, so I need to put all those in together. So I'm going to do delta H. Right, so I'm going to substitute this value of Q into there. That's going to give us delta H is equal to MC delta T over N. Now, they don't call M the mass of water, they call that W, don't they? The mass of water. So I'm going to change that M for a W. We'd usually use M in our expression, probably. So we're going to do that. Now, N, I'm going to substitute that in using that. So the mass of the fuel burnt, which you're going to call that B. So delta H is equal to WC delta T divided by the mass of the fuel burned, which is B, divided by the MR of the fuel. Right, what happens is that MR is going to come up onto the top line, then we get rid of that there. And finally, what we need to do, we need to remember that this is an exothermic reaction, so we need to put a negative sign in there. Okay. Right, so which one is it then? Well, without looking at, they put them all in a different order, but you can see the only one that's dividing by B is A, and yeah, that is correct. So A is the right answer there. Okay, and that is the end of the paper.